Hello, this time I will talk on resonance in case of Lcr circuit. We have got series of inductor, capacitor and resistor and connected across an AC generator. So let me just draw it here. So this is L inductor and I'm going to draw this way. Next comes the capacitor having a capacitance C, and next comes the resistor having the resistance N. So this is a series LCR. So inductance is L, capacitance is C, and the resistance is R. So this series of three connected across a generator, AC generator, which will produce equal voltage V naught sine omega t. Okay. Now I have to talk on the resonance in Lcr circuit. Obviously, the current will flow through Lcr circuit because of the voltage you give across Lcr. The amount of current can produce is, let me say, I naught sine omega t plus some phi. Okay. It has got some phase difference, phi, with the voltage. Now, what is resonance? In case of resonance, obviously in terms of mechanics if I talk, when resonance happens, for a certain frequency which is exactly equal to natural frequency, the amplitude of the body vibration is maximum. In case of electrical resonance, it is not the amplitude, it is the current which becomes maximum. So now the current flowing through Lcr circuit becomes very maximum. Now obviously the Ohm's law says that V is equal to I into R. Now it is not a resistance only because of resistor, it is because of all Lcr. So resistance, that means opposition offered to the flow of current, is not only because of the resistor, is not only because of the capacitor, is not only because of the inductor, it is a combination of all three in series. So now V is equal to not IR, that means R is the resistance. Now it is something called, we call it as Z, where Z is called impedance of Lcr circuit. This Z is an impedance, which is again a resistance offered to the flow of current because of the combination of Lcr. And the expression for Z is given by square root of R square plus XL minus XC whole square. Now Z has got the resistance due to all three. R is a resistance because of the resistor here. The XL is actually called inductive reactance, which is equal to omega L, where omega is actually angular frequency 2 pi f, and L is inductance of the coil we use here. And this XC is again a resistance offered to the flow of current, that is because of the capacitor, we call it as a capacitive reactance, and it is just 1 by omega C, where again omega is angular frequency, C is the capacitance of the capacitor we use here, and of course the term R appears here, which is the resistance of the resistor over here. Now this is actually resistance offered to the flow of current due to Lcr circuit, V is equal to IZ. Now this Z is equal to V by I. Okay. Now we tell that at resonance, that is electrical resonance, the current flowing through Lcr circuit is maximum. That means the current flowing through Lcr is maximum. Okay. In the same way, when I say that current is maximum, I can say that the Z is minimum. Z is minimum because I and Z are inversely proportional. When current is maximum, obviously the resistance becomes minimum. So the whole term, that is square root of R square plus XL minus XC whole square, is just minimum. Now I have to get a condition for the resonance for the Lcr circuit, combination of inductor, capacitor and resistor, and the whole term, the resistance term, is actually minimum only when these two are equal. So you can make the whole term as minimum as possible when you make XL is equal to XC, so that the whole term becomes 0 and R square, and actually the total term is minimum. So XL is equal to XC, that means the inductive reactance is exactly equal to capacitive reactance of the resistance offered from the capacitor and the inductor are same. So I have got expression for XL and XC here. This is a condition for resonance at resonance. And I define some frequency, let me say omega naught, that is a frequency, we call it as resonance frequency, At resonance, obviously current maximum, Z minimum, XL is equal to XC. So now XL is just equal to omega L. I told you at resonance I use omega naught, which is equal to XC, that is 1 by omega C, omega naught C. Now I have to find out the expression for resonance frequency, angular frequency as well. So omega naught square is equal to 1 by LC. So omega naught is equal to 1 by square root of LC. Okay. And this is an expression for angular frequency. This is obviously at resonance. And if I want to find out what is a resonance frequency, so F naught is actually 1 by 2 pi square root of LC, because omega naught is just simply 2 pi F naught. So this is an expression for resonance frequency. So I can tell that when the current in the circuit becomes maximum, the resonant frequency is just 1 pi 2 pi square root of LC, and the resonant frequency depends on the value of the inductive reactance you use here. This inductance of the coil and as well as the capacitance of the capacitor. If I draw the curve, actually you can increase or decrease the frequency. So this is actually frequency along the x-axis. And I'm going to find out how current changes with the frequency. Obviously, for certain value of current that we call it as F naught, we call it as resonant frequency, the current becomes maximum. That means for F naught, the current becomes maximum. In either side, if you increase or decrease the frequency, current actually decreases. So this way you can expect the curve. So for certain value of F naught, the current becomes maximum, that is I naught. So I naught is equal to V naught by Z, where V naught is again, it is a peak value of voltage by impedance from LCR. If I draw the curve for Z versus I, actually this is for I versus F, and if we draw the same curve for F, and it's this along the y-axis, it is a Z, and for some frequency we call it as the resonant frequency, that time the current was maximum, at this time the impedance should be minimum. That is what condition we obtain here. So it's a minimum here, and it's this the way we get the curve. So thank you for watching this.